So, just a reminder, we've got the lab pilot today. We'll do checkout, and then we may do an hour and a half after the max and those. Remember to bring your lab notebooks this afternoon, and on Wednesday we'll take exam report. Then get those back on Friday, and then we'll talk about things on the review for that. So the last chapter, really it's mainly chapter 23, and we're just going to kind of touch on the things that are on chapters 24 and 25, the units over chromatography. And chromatography is certainly a powerful tool used in analytical. A lot of the things that are in the videos, we're going to leave that for the videos. That's where I did a lot of the background stuff. I want to just talk about, for the most part, explain some things in more detail and working a few problems. So, partitioning, solvent extractions using a set foam. Something that almost everybody in chemistry does. We're going to talk about the math of that a little bit. And then just breaking down chromatography a little bit, just to give you an introduction to it, the types of some of the key equations that we use, water chromatograms, efficiency and resolution. So those are ways that we can adjust to try to get a better separation. And then there's just going to be about, I think there's less than 10 slides each talking about Chapter 24, which is just an introduction to gas chromatography, and Chapter 25, which is an introduction to high-performance liquid chromatography. Again, I strongly encourage you to take a look at these exercises at the end of Chapter 23 and the suggested problems in Chapter 23 as well. I don't think I gave you any particular problems out of Chapter 24 or 25. So the first thing we're going to talk about are solvent extractions. Solvent extractions where you have two admissible phases and you have a solute distributed, or partitions in between those two phases. And the goal for doing these is to isolate or to concentrate a particular species that we're wanting to analyze. You did these for a isolation step to purify your unknowns in organic. We commonly do it to remove interferences in analytical, to try to get the compound we're looking for separated from a lot of other things so we can do a better analysis in the long run. So commonly we're trying to remove these interferences that would be a problem for us, try to block those out. So whenever you're trying to do a phase separation, you have an equilibrium distribution. And if you have two admissible phases, we give this one called the name, the partition coefficient. This is the name of that equilibrium distribution constant. And it's defined as K, capital K, same as before. It's the concentration ratio between the two phases. Okay, so you've got phase 1 over phase 2 that you describe it. And you really have to say what's phase 1 and phase 2. You can't just say it's the top layer versus the bottom layer. Usually we think of it in terms of a ratio of organic versus aqueous, if that's the separation that's done, but we also do other types of partitions. So usually with organics, what's the heaviest layer, the water or the organic? Which one's on the bottom?
Water.
The water's typically, if you've got something like ether, toluene, those all have a density less than 1. But if you start looking at halogen solvents, fluorinated solvents, now they get densities much higher than 1, they'll switch them. So the best thing you can do is define what your ratio is. You put one phase dash the other phase so you know which one's on top. Okay? So a lot of times it's implied, though, that water is the bottom phase. Just here's a couple of examples of something you may be asked to do. And on the final exam, as much as something that I would expect you to do as well, you've got a compound for certain, and you've got a certain mass of it in water, and you're going to extract it in a equal volume of isopropyl ether. So you've got 735 milligrams initially. It's in 100 mils of water. So I tell you, it's an equal volume of isopropyl ether, so it means there's 100 mils of it as well. And you're going to have a separation of this compound in between those two phases. All right, so you're going to have If you want to think of it, the way you're probably going to do this is in your subfunnel. So you're going to have an aqueous layer down at the bottom, and you're going to have an organic layer at the top. And you know what you start with in the aqueous layer, 735 milligrams, and I want to know how much is going to end up in this organic layer. Okay, that's typically what I'm trying to solve. But in this case, it tells me that after we shook it up, we took the amount of residue that was found in the ether. So the layers were separated, the ether was evaporated off, and that ether contained 585 milligrams of the compound. What's the partition coefficient? So what we want to do is find out what is K in this one. So K is going to be defined as the concentration of Q in the organic divided by concentration of Q in the aqueous. Okay, now, usually when we think of concentration, we think of it as molar concentration. So we would need to know molar mass to calculate what the molarity is. The key thing about K values are unitless. Okay, so partition coefficients, any expression of concentration that's the same on top and the bottom, it doesn't matter if it's percent, if it's straight mass, whatever it is, it's going to cancel out. So we can use any combination. If we had moles times volume, mass times volume, whatever we had. So in this case, we've got mass. So if I had 735 originally, and that means that at the end I've got 585 went to the aqueous, how much is left in the organic, or in the aqueous phase? This went to the organic, I should say. So this is the ether phase. How much is left in the aqueous phase? Okay, so there's 150 milligrams left. So that's the way I'm going to take concentration is equal to my mass times my volume divided by mass times the volume. In this case, the volumes are the same. So the 100s cancel out, the milligrams cancel out. It's a little bit less than 4, so 3.8. What do you get? 185 divided by 150. 3.9. Okay, so K here is 3.9. Finding K. So sometimes they're going to ask you to find K. Sometimes they're going to ask you to find the milligrams. There's some more examples of these problems in those exercises in the back of the book. Got the hiccups. Okay, so chromatography is now where we're going to do these types of separations. Now our two different phases that we're using, instead of being two immiscible liquid phases, you've got one phase that's moving called the mobile phase, moving at a fixed velocity, and then you have a stationary phase that's not moving. Okay, and it's typically fixed to a column in some way. The mobile phase can either be a gas or a liquid as we're treating it here. And every time the solute migrates down the column, it's basically undergoing a partitioning event, a repetition of what's happening in a set funnel over and over and over and over and over. Okay, and that process is called elution, as you get something to get it to migrate down the column. All right, this is an example of the earliest chromatography that was done. Chromatography was invented by a Russian biochemist named James Titwit. And Titwit was trying to isolate out chlorophyll because he noticed that when they took the chloroplast material and depending on how it was left exposed, sometimes he'd come and pick it back up and it would be green after a weekend, and sometimes it'd have more of a red color to it, sometimes it'd have a yellow color to it. So he thought, well, maybe this is a mixture of things. And there's one of the things saying is that Some was actually just accidentally spilt on a piece of chalk. And as the chalk absorbed the ether and started to, like a wick, migrate up the ether, then it started to form color bands. Some people say that that's a folklore legend of how it was. He came up with the idea to do it. Whatever it was, he took chalk, ground it up, put it inside of a column, and he used calcium carbonate in his actual experiment. And then on the bottom, he had calcium hydroxide. And then he had a filter, some type of a porous plug put down the bottom so the solids couldn't pass through. He loaded it with solvent, and then he put his compound on the top, which is a plant extract. And as they started migrating through, the two different things migrated at different velocities, so that the first component came off the column first. So component B migrates the fastest, so it came off the column first. He collected it, and then he got compound A off of it. And if you stopped it at a period of time, you'd see all these different bands that were representing the different components that he was separating out of the plant extracts. That's our first documented case of using chromatography we have in history. So of the chromatography, there are 5 major mechanisms of chromatography that you need to know. So make sure you review these in the video. Absorption chromatography. This is typically what you did with thin layer chromatography, like an organic. The solute absorbs onto a surface. That was going to be the experiment we did last week, but with TLC plates, and I decided not to do that, so we could just finish some notes. Partitioning chromatography is where you have 2 immiscible phases, so there's actually a liquid embedded on top of a surface support, so it's still a liquid extraction. So if you want to think of it in partitioning, you have some type of a support material that's got a thick liquid on the surface of it, usually a very, very thin layer. All right, so those are the first 2. The next one is ion exchange. It's where you separate things based on an electrostatic interaction between a charged stationary phase and a charged solute. And the idea is opposites attract. So if you want to separate out cations, you use an anionic stationary phase that's negatively charged. So it'll pull those in. All right. Depending on the degree of interaction is going to be based on how hard or how soft an ion is. And if you've had inorganic, you've heard those terminologies, but basically the hardness of an ion is the more charge it has, the smaller it is. That's a hard ion. A soft ion is large with a low surface charge density. Okay, so the things that have their softest are going to elute off the column first because they have less interaction with something that's a harder ion. So based on that, we could separate things like the halides from one another. You could separate sulfate from sulfite, SO4 2- from SO3 2-. All types of ion separations. Molecular exclusion, so also called size exclusion. Now you're doing separations based on a pore size. So the separation is based on molecular entrapment. It's based on the size of the molecule. So the idea with this is that you have some type of a pore or network that large molecules can migrate through or can't migrate through. Their access is blocked for the large ones, but the small molecules can get embedded in here. It's good for separating out very large from very small things. So if you wanted to separate out a protein monomer that weighed 80,000 from the dimer or trimer that weighed 160,000, okay, so you double the molar mass, you can separate things like that very easily. If you wanted to separate things that weighed less than 1,000 from all the proteins that weighed over 20,000, this is the way to do things like that. So if you want to separate large from smalls, that's a good technique for it. Now, it's not suited if you wanted to separate 2 peptides, let's say, that were decamers, 10 amino acids in it, that was one amino acid versus another amino acid. To get effective separation in molecular exclusion, we look at things that are at least 10% different in molar mass. So if you're looking at something that's amino acid difference, you're looking at very small changes. So it's not, with that, you're going to go to typically partitioning chromatography. Now, the last one that's it's introduced in the book a little bit is probably one of the most powerful ones today because it really lets us look at very, very specific interactions, affinity chromatography. Now we're looking at molecular shape and the same type of a lock and key mechanism that we talk about that occurs with enzymes and a substrate. So there's some shape that's we're looking for to interact with in terms of something associated with the stationary phase, and whether it's this pocket in this one that we're looking to recognize, those are the things that adhere to the column, and everything else just flushes on out. So this is a great technique to use to pull the needles out of the haystack. All right, you've got 10 other things, 10,000 other things there, and when you start looking at samples like biological samples, if you just look at your plasma, okay, if you take your blood, you spin it down, you get the red blood cells, and get the plasma off the top of it, you can measure 10,000 different compounds in that plasma. And there are a lot of different substances in there. Some are there at like the common ions that are there, the common proteins that are in there. Those are going to be there at the 10% level. But then once you get down to the trace level, less than micromolar, there are tens and thousands of other things there. Okay, very small peptides, all types of intercellular material that you see. So the tables that I've went over already in the notes, they summarize the things that I've been talking about, the different types of chromatography. So let's just to make sure we're here today. So which one would you use to separate out these two ions? Okay. Well, almost everybody got it. So I actually just told you this exact pair in my example. So we've got two ions that have the same charge. You're going to separate ions with exchange chromatography. So small inorganic species, that's the way that we go with. So we look at in chromatography, we try to have the mobile phase moving at a constant rate. Now that's why I say some forms of chromatography different from one another, and that's one of the challenges that we have with thin layer chromatography. So if you remember with thin layer chromatography, since we didn't do the experiment, you're going to have to refer back from other experiences that you did. But the solvent starts moving up the bottom of the plate pretty quick. And the further that's being drawn up by capillary action, the more and more the solvent slows down. So to go up that last 20% of the plate that you let it develop up takes longer than it took for it to go the previous 80%. Okay? So on that, the mobile phase velocity is not constant. The types of chromatography that we like to do for analytical, we keep that at a constant velocity. Okay, so we pump it in a way that the velocity of the mobile phase is not moving. Woo! Okay. Yeah. Back there way. So when we've got this constant mobile phase, that gives us some predictability. A chromatogram is just defined as a plot of the detector response versus time, and we identify the time of each component as the retention time. So that time, if we want to relate it back to volume of the mobile phase, all we have to do is know the velocity and calculate that. Now in the book, the textbook uses the term to represent the void time, how long it takes an unretained species to migrate down the column. It uses T sub m for time of the mobile phase, and I use T naught for represent not the void time. So we'll exchange those two. So just realize that T naught and Tm mean the same thing. So the readjusted attention time is simply the difference between the retention time and T naught, and that's relative to any given solute. If we look at what we call the selectivity has the Greek letter alpha. It's the ratio of the adjusted retention times, and this number is always going to be greater than 1. All right, so it's always greater than 1. So we put the last eluting one on top when we define these things. So it's just the ratio of the adjusted retention times, or the retention time of the last eluting. So this is going to be the last eluting, divided by, or less T naught, divided by the first one, less T naught. So probably the way that you typically going to see those would be a 2 to 1. So the second one over the first one. So your selectivities are going to be greater than 1. If two things co-elute, the selectivity is 1. The capacity factor is a common way that we report retention. So this is similar to what you did with the ratio, the RF value that you did with thin layer plates. The capacity factor does a similar type way to normalize. So the reason you did RF with thin layer chromatography is that if you ran it and let your solvent go 8 centimeters and somebody else let it go 10 centimeters, you could do a comparison to find out if the RFs are the same at the same compound. This is something similar. So if I ran something on a 10 centimeter column, somebody else uses a 25, it's the same stationary phase and the same solvent, it should have the same K prime, capacity factor. So capacity factor is the thing that takes into account the length of the column. So what it is the adjusted retention time. So TR less T naught divided by the void time T naught. So you'd simply take what is the time of a peak that you're looking at, whatever its time is, less the T naught time. Okay, so something that's unretained, subtract those and divide by T naught. So these things are always going to be positive. Okay, so they have to be greater than 0. So now how positive can they be? They can be from right at 0. If it's unretained, it's 0. But 0 is to something that never comes off the column. Completely retained could go up to infinity. You can change conditions where something doesn't elute off to a column in days. All right, that's pretty worthless for us, but sometimes that occurs. So if we look at the capacity factor, and we look at these ratios that we have, capacity factor tells us how much time something spends in the stationary phase relative to what it spends in the mobile phase. So selectivity, we said, was the ratio between two different things. It's the ratio of K prime to its neighbors, K prime. So if we look at what K prime means in terms of the mathematical terms, it's equal to the concentration times the volume in the stationary phase over the concentration times the volume in the mobile phase. So concentration times volume is equal to moles. So moles in the stationary phase divided by concentration times volume moles in the mobile phase. Now the ratio of the concentrations is our definition of what our partition coefficient is that we talked about just a few slides back. So this becomes K prime's a ratio of the partition coefficient times the ratio of the volume of the two phases. So I can change the things in the stationary phase, and it's going to change K. So if you can imagine that I had a column that had if we're going to look at, think about if it's a thin wall phase. So if I got a phase that's this thick, so this represents my stationary phase. And I've got my solute that's moving down this column. All right, so everything here represents the mobile phase. And whatever the ratio to the units of volume are, so whatever this volume is, if I take a cross section of this, and whatever this volume was, this would represent the volume of the mobile phase. And this guy would represent the volume of the stationary phase. So if I were to increase the size of this stationary phase, so make it a little thicker, so its volume increases. So this volume goes up, the other one's got to go down in the cross section. That means I can adjust the retention on it. So it's a way that we can tune our separations. We can get things to stick to a column more or less by controlling the volumes a little bit. Okay? Another way to look at this selectivity that we defined on the previous page, we said it was the ratio of the adjusted retention times. It's also, if you put the K prime ratios over the top of each other, you just cancel out the T naughts. And now if you express it in terms of the volume of the stationary and mobile phase, those two things cancel out. It just becomes the ratio of the Ks of the distribution coefficients. So these things are all related into understanding what's happening in your different separations. So here's a type of problem I might expect you to do in the book, or on the exam, as well as the final exam, I expect you to do it. So you get this separation. Here's the void time. Here's a couple of different components that elute off the column. So this plot of chromatogram versus signal is the void time, and I want to know what is the capacity factor of compound A. So what is the K prime for compound A? So it's simply TR less T naught divided by T naught. A key thing you have to look at is the units the same between the times. So especially if something's eluting really fast, they may give you this in seconds. You got to make sure your units are right. All right, so, but on this case, everything's given in minutes. So TR is 3.37 minutes. The void time is 1.21 minutes divided by 1.21. So whatever that value comes out to, that's what K prime is. Now selectivity, the way that I do selectivities is that the ratio of the adjusted retention times. So it's TR of the second eluting peak less T naught divided by TR of the first eluting peak less T naught. So I take the second eluting peak, so 413, less the void time, and the second eluting peak on the bottom less the void time. So those are really simple calculations to do. You just have to know the numbers to put into them. All right, so we are writing down. All right, so this one comes out to 1.79. And this one comes out to 1.35. Okay, so the bigger the number of selectivity, you want a relationship question out of this. Just some ways to think about this. The larger the K prime, means the greater the retention time. That means the longer it's sticking on the column. The larger the selectivity, the greater the difference in retention times. Selectivity is a measure of how far these two things are apart from one another. And selectivity gets closer and closer as it approaches 1, those two things merge as a single peak. So selectivity of 1 means the two things are on top of each other. Right? So the bigger that number is, the better. Right? There's a limit to bigger is better. Okay, so resolution is the major term that we use to describe how good the separation is working. So resolution is a measure of the effective separation. And there are two major factors that contribute to how well things are separated in chromatography. And those two things are, what is the difference in the retention time of the two peaks? So like we saw on the previous page, how far are these two things separated from one another? That's number one. The second thing is, how broad are the peaks? How wide are the peaks with reference to one another? Because the wider their peaks become, the poorer the separation is. Those two peaks can spread out so that they have overlap. And we define resolution as the difference in the retention times divided by the average width at the base. So when we define it in this one, it's defining as the average width in the base. So average width at base. Right. And another way, because width at the base is kind of hard to measure because these are Gaussian shaped peaks. They don't make these perfect triangle type shapes. So the real peak shape is what's shown here, is they bleed out like an exponential curve shape on each side. So it becomes a little difficult to say, well, where exactly is the end of the base at? So we typically go up some certain height to make the measurement, and a common places that we do the measurement is the width at half height. So however tall the peak is, you would go up to 1/2 of that height, and now you can pretty easily measure the width of the peak. Okay, so to calculate resolution there, we just have a formula we plug in. So we've got this constant number, the difference in the peak times divided by the width. Now here's where you have to really be careful when you look at the scale, because when you blow one of these things up, typically this is going to be in seconds. Okay, you describe a peak as so many seconds wide at half height, but when you describe retention times, it's going to be in minutes, and you have to make a match. They have to be the same. So you can take both of them to minutes or both of them to seconds, it doesn't matter. They just have to be so they cancel out.
Are you taking the slope that half height there, tracing that line down to the x-axis?
No, all I'm doing is, well, you're comparing to the x-axis, but you're just going halfway up and then measuring how wide is this.
Yeah, I just saw the dot there.
Well, but it's not dropping down.
Right.
Yeah, the dotted line going across is just going to half height. Okay? All right. So here's an example of an exam question. And just, I'll tell you, so something you can do for, as you're reviewing for the final. This is kind of the chapter I told you all, just to remind you, last year's test didn't have any chapter 23 on it. The year before had some. This is the chapter I didn't miss. So just because you pick up a test and don't see any there, don't mean that you're not going to have none. So you're going to have some of these types of calculations. So certainly, if you have to go back 5 or 6 years with a test, look at some reflective questions. So two compounds were separated by gas liquid chromatography. Retention times were 628 and 642. I give you the peak widths at half height and find the resolution of the two compounds, and are they well resolved. So let's just crank through this one. So we've got the everything's in seconds, so that helps me out. And here's my equation that I'm going to use, because I've got the peak width at half height, so that's the one that I want to use. So resolution equals 0.589 times the difference in the retention times. So the last eluting less the first eluting, divided by, at the bottom, the average width at the half height. So I'm going to take those two times, those two widths, and I need to average those two together. So at the bottom, when I average them together, I get 8.85. We'll keep that in there so we don't get a rounding error.
more concerned with us being able to work these equations or kind of understand the relationship?
Both. Yep. Yeah. No. No, I want you to be able to do, these are pretty straightforward equations. If you write them in your note card, I want you to be able to use them. But in the same terms, I want you to understand what they mean. Okay. So I get a resolution, if I did the math right, of 0.932. Okay. So, and then I asked the question, are the peaks well resolved? Well, this is where you would have to know something about what resolution means and what the different number means. So you'd have to have knowledge of this slide. So here I give the example of some different resolutions and what these effective separations are. So here's a resolution of 1/2. And if I look at this, this would appear as a single peak. And if I had knowledge of the chromatographic system, the bandwidths are typically from one component to the other are reproducible. So if this is the peak width that I would expect to see with, let's say with one band, one component, this peak width. If I looked at this guy, I would know that that's more than one peak because it's too wide with respect to its height. So anybody that's, if you had a couple of peaks there and the one next to it was only this wide, you'd know something's wrong. Okay, so this is multiple peaks that are colluding here. But in this one, they're not even separated so that there's only a single maximum. So if you go up to a resolution of 0.75, at least now it pulls it out and you see two different retention times out of it. When you get to a resolution of 1, your overlap is less than 10%. Our goal is to be a resolution greater than 1.5 because 1.5 has less than 3% overlap. Okay, so we have less than 3% overlap.
What's the resolution value last slide?
So it was a little bit less than 1. So a little bit less than that. Is this a great separation? Not great. Yeah, not have overlap, but it's not bad. I mean, you could, if you were trying to isolate these compounds for some of the analysis, you could take a plug that went from here and then start collecting another one. You can still get the bulk of those compounds as pure compounds. Now, integration with systems today, computer systems that take these, they will mathematically model this and they will calculate these peak areas independently. So they can deal with resolutions. Most systems can deal with anything with a resolution greater than 0.6 and do a pretty accurate calculation. It depends on the software that you're using to collect the data with. Typically a perfect goal is 2.5. But when you go beyond 2.5, you're using a lot of solvent and not getting much good out of it. All right, so the quality of the separation, one of the problems that you have in all forms of chromatography is that when things migrate down the column, they start to spread out. And that's due to diffusion that occurs, as well as a few other things. Same way if you took a drop of a dye, and if I got a glass of water and let it set still, and if I take a needle and put a concentrated drop of dye in the center, slowly pull the needle out, that drop of dye is slowly going to start to diffuse over the course of time and spread out in that container. The same thing occurs if I start a plug of sample and it starts migrating down the column. It's going to start spreading out and get wider and wider and wider so that the concentration is decreasing as it spreads out as a function of time. That's a problem that we have in chromatography, is that you start off with a very, very sharp peak to start with, but as you start running longer and longer times, so you're 26 minutes into it, your peak width's more than double. That's that peak trying to diffuse out. So that's a factor that we're fighting. Part of it's due to just molecular diffusion. Another part of it's due to mass transfer effects. So you've got the solute transferring in and out of between the mobile phase and the stationary phase. And what happens is that if you want to think of what's going on with a particle at a molecular level, so you've got a particle here, and you've got a solute molecule that was in the mobile phase moving along, and it decides, hey, I'm going to partition in the stationary phase. While it partitions in it and is stuck to the surface, all of its buddies go, wee, we're going on down the column. Okay. So it takes, every time one of these phase transfers occurs from the mobile to stationary, that takes amount of free energy to accomplish that. So it has to gain energy from the environment to go in, energy from the environment to go back out and start migrating down the column again. Until it's released from the stationary phase, it can't go catch up with its buddies. But every one of its buddies are doing the same type of thing too. But depending on the kinetics of mass transfer, that can cause if the temperature is not right, basically, it causes your bands to separate even further. All right. All right, and efficiency is another measure of simply how sharp your peaks are. If we look at efficiency, the way that we typically represent that is a term called plate count. So plate number is a quantitative measure of how sharp your peaks are. And we define this as the number of theoretical plates, and our goal is to have this number maximized as high as possible. If you've got the width at the base, it's 16 times the retention time squared divided by the width at the base. Again, half height is the most common one we use. So it's 5.55 times the retention time squared divided by the width at half height squared. And with the key with this one, as with the other ones, make sure the units of time are the same. Same units. All right, so we want those two things to be maximized. Now, another thing we look at to tell us if the system working in a way that we expect it to work, are the peaks symmetrical or not. So ideally, we have things that are symmetrical. So the asymmetric measure is the measure of the deviation from Gaussian shape. So when I look at a peak and I see that, I typically do a measurement at 10% of the height. Okay, so I take the height of the peak and go 10%, and I would draw a line from the point of maximum signal and drop down, and then measure the width on the front side versus the back side. And what we see on this one is that there's a lot more width at the back side than the front side. That's a peak what we call tailing. And this is an indication of non-ideal conditions. So in the perfect world, it's perfectly Gaussian. A equals B. Right? But the fact that things are moving, it's rarely going to be that. Okay? So, and if you overload the column, you can make it go the other way. If I put more sample on the column than the column has capacity to deal with, my peak shapes may start looking like that. Okay? And now I would have a fronting peak, where B would be a lot larger than A than what we had in this case. That measure tells me something about what's going on with my system. All right, so I'll show you how to do a plate calculation. So in GC, you've got something that elutes in 325 seconds. The half width height is 5.12 seconds. Tells me the length of the column, how many theoretical plates did this column produce. So you just have to know the equation to pick up. I tell you the width at half height. So that's the one that we're going to use. So I need to use this in the equation. So it's the 5.55 times the retention time squared. So 325 seconds is the retention time. All right. Divided by the width at half height, 5.12 seconds squared. And these are seconds in both, so you see they're going to cancel out. So it's just popping the numbers in. I get, so this is the number of plates that the calculation spits out at me. But if I think about it, I've got it 3 significant figures. So I'd need to say, 2, 3, 4 times 10 to the 4th. Plates.
Confused what plate is.
Say again?
Kind of confused what you mean by theoretical.
Okay, and I talked about this in the videos. A theoretical plate is the distance that something has to move before partitioning event occurs. And what we want it to do is to be minimize that distance, so we want the maximum number of plates. So the plate height is equal to the length of the column divided by the number of plates. And again, these are theoretical. You can't see how far this is. This is a way that we're modeling what we think this is going to be. So if we looked at what is the plate height with this one, we've got the length of the column if we wanted to calculate that. So we'd simply put in the length of the column. And divide it by the number of plates. And we would divide that out to find out that number is about roughly a half, whatever it is. Okay, so in this case, it's in centimeters. It'd be about half of a centimeter. Now, I know you're thinking, well, this is crazy. No column's that long. Okay, so if I think about what that is in meters, that's 115 meters long. We've got a 150-meter column that Dr. Pila uses to separate stuff downstairs. So in GC, the gas goes through a little fiber, and you wrap this thing around, and yeah, a common length that you use is 30 meters. It's a standard length. So yeah, we do separations across extremely, extremely long lengths. Imagine having a TLC plate that's 115 meters long. Okay, so that's effectively what type of separation that we're accomplishing. And we can do this in an hour separation. So using instrumentation and having a constant flow rate across it, we can get some very, very high resolution separations in systems. But the goal for this, in terms of our numbers, what's good versus bad, that's the important thing. You want this plate number to be as high as possible. That's your best separations. Or if you get the plate height, you want the plate height to be as small as possible. Okay, so they're inversely related. Okay, so that resolution equation that we talked about earlier, I tell you what, I want to spend just a little bit of time on this one, so I'm not going to tackle it in the last minute. So this is where we'll start back up this afternoon. All right, so y'all want to do 130, 115? Y'all need
130.
Okay, 130. So see you at 130.
What the things on spreadsheets lose or take their
Okay, fine.
You don't want to just insert the
Don't just stick them in there. Staples, if you put a bunch of staples in there, the pages start getting hung up. I prefer tape or glue or staples.